Alright, crazy kids, here's your lecture on nuclear chemistry. So a long time ago, a Frenchman accidentally discovered the spontaneous emission of rays or particles from certain elements. He called the spontaneous emission of rays or particles from certain elements radioactivity, or radioactive decay. Specifically, the rays and particles that are emitted from a radioactive source are called nuclear radiation. And nuclear reactions begin with unstable isotopes we call radioisotopes, and atoms of these isotopes become more stable when changes occur in the nuclei. So, what you have here is an atom. In the center of the atom, the nucleus is unstable. To become stable, it spits out nuclear radiation. And there are three different types of nuclear radiation that can occur: alpha, beta, and gamma radiation. So it's alpha, beta, and gamma. Alpha radiation is the same thing as a helium nucleus. And it's dictated by He42. Think about helium. It has 2 protons and 2 neutrons and 2 electrons. Kind of looks like this. So we're talking about just the nucleus, so we're going to remove those electrons. And what's left is what we call an alpha particle. Take note that the mass number, protons and neutrons, is 4 particles here. And your atomic number, 2, meaning you have 2 protons. That's how it works. Your penetrating power here is very low. You're only able to penetrate about 0.05 millimeters into tissue. So not that dangerous. Your clothes can block alpha particles. Not that crazy. Your next type is going to be beta radiation. And beta radiation is a high energy electron. And its symbol is going to be E0-1. Penetrating power on this is going to be medium. This goes about 4 millimeters into tissue. So more dangerous than alpha particles, but not overall that terrible. What is beta radiation? Well, an electron results from the breaking apart of a neutron. So a neutron breaks apart into a proton, which remains in the nucleus, and a fast-moving electron is released. So we start with a neutron. Ooh, that 0 looks pretty bad. Let's try again. And that breaks apart into a positive piece called a proton and an electron. This is what a nuclear reaction really looks like. And the important part is to have it balanced. When we balance chemical equations, everything on the left have to equal everything on the right in terms of number of things. When you balance nuclear reactions, your total mass number on the left has to equal your total mass number on the right, and your total atomic number on the left has to equal your total atomic number on the right. So here, for my mass number, I have 1 on the left reacting, and I have 1 on the right being produced. And for my atomic number, I have 0 reacting, and I have 0 being produced. Remember, you're adding them all up. That's how it works. Let's show you an example of that. So it says here, carbon-14 is a radioisotope. So it's not stable. Something has to occur to make it stable. It emits a beta particle as it decays and forms nitrogen-14. So we start with carbon-14. So carbon-6, 14. It emits a beta particle, so E0-1. And what's left over is nitrogen-14. Notice how on the top, my mass number, I have 14 and 14. Those add up to be the same. And my atomic number, I have 6 and -1 and 7, which equals 6 as well. So once again, what's occurring there is you have a neutron changing into a proton and spitting out a high-energy electron. Kind of crazy. Another dead giveaway that this is a nuclear reaction is I start with carbon and end up with nitrogen, a totally different element. All right, so that's kind of what happens. And then I think I wrote out this here. Nitrogen-14 has the same mass number as carbon-14, but its atomic number is increased by 1. It contains an additional proton and 1 fewer neutron. All right, the nuclear equation is balanced. So once again, to balance it, your total mass number on the left has to equal your total mass number on the right, and your total atomic number on the left has to equal your atomic number on the right. You're adding all the pieces put together. Gamma radiation is our last type, so gamma radiation kind of looks like that. It is just a very high energy electromagnetic radiation, specifically a high energy photon emitted by a radioisotope. The penetrating power here is very high. It's so high that it'll just pass right through your body and you won't even know it. All right, so this is a gamma particle, goes right through you, no big deal. They have no mass and no electrical charge. The emission of gamma radiation does not alter the atomic number or mass of an atom. which is kind of crazy. So I could have something like, oh, I don't know, uranium-238, and it could emit gamma radiation and stay uranium-238. No change in the mass number, no change in the atomic number. Just gamma radiation is spit out. Very, very high energy electromagnetic radiation. All right, those are your 3 types of nuclear radiation. Let's do the next part here. Nuclear transformations. So all atomic nuclei, except for hydrogen, consist of 2 or more protons. If a force did not hold these subatomic particles together, the like charges of protons would repel each other and we would fly apart. So if I just take a look at helium, right? Helium has these 2 electrons on the outside, and then inside the nucleus itself, once again, we have 2 protons and 2 neutrons. These 2 positive charges should repel each other and just fly apart, right? But they don't, because what we have here is a nuclear force. It's a force that acts between all nuclear particles that are extremely close together, such as protons and neutrons. At very short distances, it is stronger than the electromagnetic repulsion of like charges. So the nuclear force holds all these things together. However, we have stable and unstable nuclei. The stability of a nucleus depends on the ratio of neutrons to protons. So it can mess up the nuclear force if you have too many of one or the other. For elements of low atomic number, it's about 1 to 1. So for every proton, you also have about 1 neutron. They can match each other. Above atomic number, now we have more neutrons to protons that make it stable. Some nuclei are unstable because they have too many neutrons compared to the number of protons. And other nuclei are unstable because they have too few neutrons to the relative number of protons in the nucleus. These nuclei increase their stability by converting a proton to a neutron. So I could have the conversion of a proton to a neutron or a neutron to a proton. Both are possible. And it's important to note that all nuclei that have atomic number greater than 83 are radioactive and will undergo radioactive decay. Just how it works. So we showed you up here, right? This is the conversion of a neutron into a proton, beta radiation. However, down here, we have something called electron capture. So it's not the same because you're capturing an electron instead of spitting out a high energy electron. So here we have our nickel capturing an electron, turning into cobalt. Notice how when you capture that electron, one of the protons turns into a neutron. I know that because my protons, I have 28 and I only have 27. So I'm losing a proton, but my mass number is staying the same at 59. So a proton turned into a neutron. Kind of neat. Here's another example. I can tell that this is electron capture. First of all, because an electron is a reactant, not a product, like it was with beta radiation. And then secondly, looking at our number of protons compared to number of neutrons, I go down in terms of my number of protons, but my mass number stays the same, so a proton turned into a neutron. Another thing could occur, a positron emission. So a positron is a particle with the mass of an electron, but a positive charge. So it's kind of like the opposite, kind of weird. Its symbol looks like that. So I would actually write it like this, +1. During a positron emission, a proton changes into a neutron, just as in electron capture. So it's very similar, except slightly different. Once again, my number of protons decreases, but my mass number stays the same. But instead of capturing an electron, I'm spitting out a positron. So those are some nuclear transformations for you guys to think about. Our last piece of the puzzle is going to be half-life calculations. So it's the time allotted for 1/2 of the nuclei in a radioisotope to decay into products. So this doesn't all happen at the same time. It takes time for radioactive decay. Specifically, we use half-lives to determine how much time it actually takes. And we'll do an example problem down here in a heartbeat. For the calculation, we use this formula right here. All right, and that means the amount remaining, how much is left of your radioisotope, is equal to your initial amount times 1/2 to the nth power. And n is how many half-lives have occurred. To calculate how many half-lives have occurred, you have the time that has passed divided by the actual half-life value. And this will make more sense with an example. There we go. So the half-life of this radioisotope right here is 5 days. It means for every 5 days, half of it decays away. All right, so here's my whole amount. In 5 days, we'll do this fancy little deletey thing. Half of it decays away into something left, and then we'll left half of it. So that happens every 5 days. So in another 5 days, half of what's there would then decay away again. And then another 5 days, half of that would decay again. All right. And eventually you're left with a very small fraction of what you initially had. So let's figure out this calculation. So it says if the initial mass of the sample is 100.0 grams, how much will be left after 30 days? So the first thing we have to do is calculate n, how many half-lives have occurred. So we have 30 days. Whoa, I don't know what happened there. 30 days divided by 5 days. Now 30 days is the time that has passed, and your 5 days is the actual half-life given to you in the problem itself. So 30 divided by 5 is 6, so we've had 6 half-lives occur. So that's the number of half-lives. And then we're going to take our initial amount, 100.0 grams. We multiply it by, 1/2 to the 6th power. And that's going to tell us how much is left over. So I plugged that into my calculator, and I get 1.563 grams. So that is how much is left from my initial 100-gram sample of my radioisotope. Only 1.563 grams of the original compound is left. The rest of it has decayed into something else. Last, we have fission versus fusion reactions. All right, one of these can be good, and one of these can be bad, or they can both be bad. That's a weird way to say it, but we'll make the more sense of that as we go through them. So first of all, fission means to split apart. Fusion means to bring together. So let's start with a fission reaction. So I'm going to be splitting something apart. Let's talk about a very common nuclear chain reaction, or a bomb itself. This is uranium-235. And what happens here is you're splitting it apart. I'm going to make some barium-142, 56, and some krypton, Kr-90, 36, and 3. Whoa, it's a terrible 3. 3. Still a bad 3. Let's try for the third time. Ha 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 ha. 3 neutrons and 1 0. So notice how I started with uranium and now I split it into smaller elements. That is what a fusion reaction looks like. I also ended up with 3 neutrons. And this is a self-sustaining nuclear reaction because those high-energy neutrons in this case would then split more atoms. And that's what an atomic bomb looks like. So this would be something bad in our world, or an atomic bomb. The opposite of that would be fusion reactions, in which I'm joining elements together. So maybe we'll take some hydrogen. That's not hydrogen, yeah. And some more hydrogen. This would be like tritium. And I can make some helium. This is what occurs in our sun. That is a weird sun. I don't want it to have one eye. There we go. All right, and that's a self-sustaining fusion reaction. The cool thing about fusion reactions is you don't have any, really bad stuff left over, or radioactive materials. This would be a very clean source of energy if we could ever harness it. We have harnessed it here on Earth a few times. In fact, we have fusion bombs and fission bombs, and both atomic bombs, used to destroy stuff. However, we haven't really had the opportunity to have a self-sustaining fusion reaction to produce clean energy for us. If we did that, by golly, we wouldn't be relying on fossil fuels and everything would be great in our world. But right now, it takes more energy to start a fusion reaction than actually outputs. So eventually, hopefully, we can figure out fusion reactions, but for right now, we don't have it quite figured out. Anyway, that's your intro to nuclear chemistry. Hope you enjoyed it and learned a little bit. We'll see you out there.